All right, ladies and gentlemen, let's go ahead and start talking about energy. The first thing we're going to talk about with energy is something called work. And before we get into that, let's make sure we remember what a force is and what displacement is. So, force. A force can be described commonly two different ways: a push or a pull, or some kind of an interaction that causes a mass to accelerate. Now, I'd like to point something out here. This interaction has to be between two or more objects. All right. Um, an object by itself cannot exert a force on itself. And there's no other object to exert a force on or receive a force that's being exerted. So anytime there's a force, automatically we know we've got at least two objects in our system. All right, so just keep that in mind. Displacement. Displacement is a change in position, but it's only concerned with the initial position and the final position. All right, the path it took to get from its initial position to its final position doesn't matter. Doesn't matter what that path was. All that matters is that initial position, that final position. All right. Now, force and displacement are both vectors, so direction matters. All right. Work. Simply put, whenever you are able to use a force to displace an object, work is being done. All right. That's the basic definition of work. A force that's force multiplied by the displacement of an object. The units are something we call joules. You can use a capital J. And this is our work equation right down here. All right. Now, what do these two little lines mean? We've seen them before, but I'll remind you. That means parallel. So when we're looking at work, we are only concerned with the parallel component. All right. The component of the force that's parallel to the direction of the displacement. So if we take a look at this picture right here, this person is applying a force at an angle. Now, if we think about this box, what direction is it probably going to move? Well, most likely it's just going to go straight to the right. It's going to stay parallel to the ground. So when we're looking at work, we're only interested in the force component that runs parallel to the ground. So that would be this component of the force right here. And that's equal to force multiplied by cosine of the angle, which is what we see right here. The parallel component of force is equal to the overall force multiplied by the cosine of the angle. So if we go back to our equation, that's where we get this FD cosine right here. Okay, the force multiplied by the cosine of the angle is equal to the parallel component right here. All right, let's do a little practice problem real quick. So a person is pushing a box at an angle, 30 kilogram box at an angle of 30 degrees with a force of 50 newtons. The box moves 4 meters in a straight line. How much work is being done on the box? Look at our previous equation, see what you can figure out. All right, here you go. We've got our basic work equation. We've got a 50 Newton force, 4 meter displacement, cosine of 30 degrees. That'll give you a total work of 173 joules. Now note, this 50 newtons is not the parallel component of the force. It is our overall force. It's the 50 newtons multiplied by the cosine of 30 degrees that equals the parallel component. All right, so I'm not using both of these. I decided to use just this part of the equation right here because it has everything that I need to figure out what the work is. All right. Now, force. The force that we're interested in. Sometimes you get different forces acting on an object or working in a system. We're only interested in the force that causes the displacement. So think about a person lifting an object straight up in the air. All right. Now, in a situation like this, the work that's being done, the force for the work that's being done is equal to the force of gravity, equal to the object's weight. But one thing I'd like to point out, the weight of the object, the force of gravity pulling down on the object is not causing a displacement. The person applying the force up is what's causing the displacement. Now, the size of that force happens to equal the object's weight, but it's not the force of gravity itself that's causing the displacement of the object. So that's just an example. Be careful when you're looking at these that you don't take the wrong force and use that in the equation. It wouldn't work, all right? Just as a little challenge, see if you can think up some different situations where the force of gravity is the force that's causing the displacement of an object. So let's practice again. A person is standing still and holding a 5-kilogram stack of books in his arms. How much work is being done on the stack of books? Well, if you recall, we had something similar to this. I had a student beginning of class start holding some books just to illustrate this very point. Well, if the person is standing still, what's the displacement of those books? Well, the displacement is 0. Since there's no displacement, there's no work being done. Well, hold on. Is it possible to exert a force on something, but there's no work being done? Well, yes, very much so. Just because there's a force, that doesn't mean that there's work being done, all right? In order for work to be done, the force that's being applied must displace the object. No displacement, no work. If our displacement is 0, everything in our equation is being multiplied by 0, so the work equals 0. This is a good example of how sometimes in physics, a certain word has a very specific meaning, and it's often different than how it's used generally in society. Work is used a variety of ways to mean a few different things just in society, but in physics, anytime we hear or we use the word work, it means something very specific. It means a force multiplied by a displacement. All right, no displacement, no work. So, really important right here. This is one of the main significant parts of work. Work changes the energy of a system. All right, now we haven't really defined energy yet. I will, but work changes the energy of a system. All right, you can do work on an object or a system, and sometimes you'll have positive work, which means that that energy was added to that system or to that object. You can also have negative work, which means that energy was taken away from that system or from that object. All right, but work will change the energy of an object or of a system. Often that change occurs in the kinetic energy, in the form of kinetic energy, which we'll talk about that later. So, simply put, energy is just the capability of an object to do work. Keep in mind, I said it's the ability, it's the capability to do work. There doesn't have to be any work going on. The object does not have, or the system doesn't have to be doing work or receiving work in order for there to be energy. There just needs to be a capability to do the work, all right? And if we remember, work is a force that causes a displacement. So simply put, we could say that energy is simply the ability to displace an object using a force. Once again, doesn't mean that the object is being displaced by a force, but it's just capable of doing that. All right, before we get into the different types of energy, we're going to take a brief. We're going to talk about power real quick. This is something that could be on the test, but odds are it's probably not. But I'm going to talk about it just in case. So, power is simply the rate at which work is done. All right. Now, if you remember, we talked about displacement, which is a change in position. Velocity is the rate at which our position changes. So, similarly, we have work, and power is just the rate at which work is done. So, it's work divided by time. The units for power are watts. You can use a capital W. This equation right here, all of them, is the equation for power. Now notice, if you compare this to what shows up on your equation sheet, it is different. You don't have all of the different parts on your equation sheet. And that's okay. What's important is that you remember how to get this, or that you just straight up memorize it if you really want to. Work is equal to a force multiplied by displacement multiplied by cosine of theta, which is where we get this from. But here we have a displacement divided by time. Displacement divided by time is simply velocity. So that's where it comes from. Let's practice. So person A runs up a flight of stairs with a total change in energy of delta E sub A. Person B exerts triple 3 times the amount of energy and does it in a third of the time. How does person A's power output compare to person B's power output? Okay, so in this one, we're not necessarily looking for a specific value. We're simply asking, it's simply asking us to compare the power of person A to the power of person B. Okay, is power of person A 3 times the size of power of person B? Is it half as big? That's what it's asking us to look at. So look at the equations that we have, see what you can make of this. All right. So first thing I did when I looked at this was these two equations. Well, we have our basic power equation, which is work divided by time. And then we also know that work equals a change in energy. Well, with that being said, we can quickly figure out the power output of person A. It's simply that person's change in energy divided by the time. Easy enough. Well, let's look at person B. Here we have the power output of person B. Now, the problem told us that this person's change in energy was 3 times the change in energy of person A. So we take this and we multiply it by 3. And we also were told that this person is able to do this work or to change their energy in a third of the time. So we take the time and we multiply it by 1/3. All right. Now here we have 3 divided by 1/3. Anytime you're dividing by a fraction, you can just multiply by the reciprocal. So we have 3 multiplied by the reciprocal of 1/3, which is 3. 3 times 3 is 9. Now if you compare right here, this part of this equation right here is the same as this right here. And this happens to be the power output of person A. Therefore, I can simply replace this part of the equation, substitute it with the power output of person A. So the power output of person B is equal to 9 times the power output of person A. That's how they compare to each other. All right. So in our classroom, we had the 5 steps to a 5, and it would go over work and energy. If you happen to have your own copy of that book, great. Look at these pages. It'll be helpful. Otherwise, if you just go to Google Classroom, you can bring up these slides. And in my notes for this particular slide, there will be a link to Flippin' Physics, where he goes over, in a video, he goes over work and energy and stuff like that. It's a pretty good review for what we've already talked about with work and power. And then it's also going to be a good introduction to the rest of stuff we're going to cover for energy. So I'd recommend that you check that out real quick. I'm going to move on. So 3 main types of energy. All right. All 3 of these types of energy are mechanical energy. All right. They're what we call mechanical energy. So first we have kinetic energy. We also have gravitational potential energy. And then we also have elastic potential energy. And I'll talk about each one of those. Let's start with kinetic energy. Simply put, kinetic energy is the energy of motion. All right. This is our equation. Kinetic energy equals 1/2 mv squared. The m stands for the mass. V stands for the velocity. If a mass is moving, it has kinetic energy. All right. I don't care how much mass or how little mass it has. I don't care how fast it's going. If it has mass and if it's moving, it has kinetic energy. All right. So here's my question real quick. Which of the 2 variables in this equation, which of the 2 variables do you think has a greater influence on kinetic energy? Mass or velocity? Well, by looking at the equation, we can see that our velocity is being squared. As such, the velocity is going to have a much greater influence on our kinetic energy. All right. So if you want to change the kinetic energy of an object, best way to do that, the easiest way to do that is usually going to be changing the velocity. Changing the mass can change the kinetic energy, but changing the velocity is going to have a much bigger influence on it. It's going to make a much bigger difference. All right. So take a look at this. I'm not going to explain how to do this one, but I will give you the answers. Let's see what you can figure out. An object has a mass, m, and a velocity of v. I want you to select all of the following that will decrease the kinetic energy of the object by a factor of 9. Once again, we are decreasing the kinetic energy of the object by a factor of 9. Look at all these options, and I want you to select 2 answers. Out of all these options, 2 of these would decrease the kinetic energy of an object by a factor of 9. So the correct answer is C and F. If we take the mass and we divide the mass by 9, that would decrease our kinetic energy by a factor of 9. Also, if we cut our velocity in third, by divided it by 3, that also would cause a decrease in kinetic energy by a factor of 9. All right, potential energy. Generally speaking, potential energy is stored energy. All right, potential energy is stored energy. And we're going to hit on 2 main types of potential energy: elastic potential energy, gravitational potential energy. So let's start with elastic potential energy. Elastic potential energy is stored energy. It's being saved for later. And this stored energy is because an elastic object, is being stretched or compressed away from its equilibrium position. A lot of kind of newer words there. So let's make sure we understand each of them. And I'll hit on some now, some a little bit later. Elastic. Elastic simply means it's able to restore itself to its original shape, its original size, its original position. All right. That's all elastic means. All right. Stretching, compressing. Compressing means that we're kind of squishing the object together. So here's our equation. I'll get to equilibrium in a little bit. Here's our equation. We use a capital U anytime we're talking about potential energy, just in general. Potential energy, capital U. Now this little s, here's how this is what tells us that it's elastic potential energy. Some people think elastic has an S in it, so that reminds them. For me, I see the S, I think of a spring. A spring is a classic example of where we can find elastic potential energy. So when I see the S, I think of a spring, and a spring has elastic potential energy. So this must be elastic potential energy. That's how I remember it, but whatever works for you. So elastic potential energy equals 1/2 kx squared. Now this equation looks very much like our kinetic energy equation. It is not the same. The variables are different. K stands for our spring constant. X stands for the displacement from equilibrium. I will talk on that in just a minute. First, which one do you think has greater influence? Okay. Now, if an object's being stretched or compressed, it's gonna have elastic potential energy. But I want to know which has a greater influence: the spring constant or the displacement from equilibrium. Well, just like our kinetic energy equation, the x here, our displacement, is being squared, just like that velocity was being squared. As such, it's going to have a much bigger influence than the spring constant. Well, let's talk about the spring constant. So the spring constant is just a measure of how elastic the object is. All right. So it's an inherent part of the material. Just like an object has mass, it's just a part of it. Mass is just a part of the object. Inertia is a part of the object. So it is with the spring constant. The spring constant helps us understand how much force is needed to stretch or compress the material. Okay. Large spring constant means you need a huge force in order to stretch or compress the material. If it's got a small spring constant, you don't need to stretch or compress it. You don't need a lot of force to stretch or compress it. It's easy to stretch or compress it. All right. Units for spring constant are newtons per meter. Now that I think about it, I'm not sure I mentioned the units for energy in general. Energy in general, it doesn't matter the type of energy. We could be talking about kinetic energy. We could be talking about elastic potential energy, gravitational potential energy. If we're talking about energy, the units for energy are joules, just like work, same units, okay? But spring constant units are newtons per meter. All right, so let's kind of get into equilibrium and what this X could represent. So the natural position of an object when it's at rest is what we call our equilibrium position. All right, we call that equilibrium. So when we see this X, The X represents a change in position away from equilibrium because the material is being stretched or compressed, all right? So you have a natural resting position, and then we stretch or compress the object so that it's no longer at that equilibrium position. That displacement from equilibrium is what this X represents, all right? So looking at this example of a spring, here we have, let's say that this is an unstretched spring. It's natural resting position. This right here would be equilibrium, this line right here. If it kept going all the way up, that would be our equilibrium position. Because this is our equilibrium position, when the spring is unstretched, uncompressed, there is no displacement, therefore there's no elastic potential energy. Now over here, we can see that the spring has been stretched away from its equilibrium position by a displacement of x, all right? And then our elastic potential energy in this case is just equal to our equation because we don't have any known values, all right? Let's look at another practice problem, kind of similar to the kinetic energy one. A spring with a spring constant of K is compressed by a displacement of X away from equilibrium. I want you to select all of the following, which will increase the elastic potential energy of the spring by a factor of 2. Select 2 answers. You got lots of options. Pick 2 of them. Well, in this case, A and B are the correct answers. Going back through the equation, kind of maybe plug these answers into the equation, see what kind of an effect that would have on the elastic potential energy, and convince yourself that those are the right answer. All right, gravitational potential energy. So before we can launch into this, we need to consider the scale that we're dealing with, because there's actually 2 possibilities for gravitational potential energy, all right? At a small scale, we're going to say that our gravitational field, which we've already talked about in a different video, we're going to say that the gravitational field is uniformly distributed. Its direction is down, all right? This would be just everyday kind of stuff, all right? We always say that gravity, the force of gravity, the acceleration due to gravity is down. We're looking at a small scale. The field is the same at all different points, all right? Once we start to get to a large scale, that we can see the curve of the Earth, the gravitational field is very different at the surface compared to very, very, very high up. When we get to this large scale, our gravitational field isn't equally distributed. So we'd say that it has a non-uniformly distributed gravitational field. And we're not going to describe its direction as down. We're instead going to describe the direction of this gravitational field as centripetal. If some of these words and things are a little confusing to you, I'd recommend you go back and look at my videos, look at the slides on circular motion and or uniform circular motion and gravitation. That'll be helpful for you. So first, we're going to look at a uniformly distributed gravitational field. So gravitational potential energy is stored energy due to a uniform gravitational field experienced by an object. If the gravitational field is uniform, this is going to be our equation, all right? This will be our equation. So any object that has height, any mass that has height, will have gravitational potential energy every time. Now, here's the thing. Height above what? When we're looking at a uniform gravitational field, a small scale, the first thing we have to determine is, what is our zero line? Where is it? Where are we going to call 0? All right? What are we going to compare the height to? We have to have something to compare it to know if the object has height. This line is the line that we compare to, all right? We call it the 0 line. The ground is a commonly used 0 line, but it's not always used. It really just depends on the situation. It depends on the problem, okay? So take a look at this picture. So in the picture shown, we have a block that is at rest on top of a table. Here's my question. Does the block have gravitational potential energy? Well, yes and no. It depends. It depends on what we consider our zero line. So if we say that our zero line is at the ground, then yes, the block has height above the ground. Therefore, it has gravitational potential energy. If we set our zero line to be the table, then no, the block has no height above the table. Therefore, it has no gravitational potential energy compared to the table. All right. So, anytime you're looking at a problem, you got to understand the context of the problem to know where should the zero line be set, what should it be compared to. That's going to help you know whether or not the object has height, and therefore whether or not the object has gravitational potential energy. So, let's look at this. An object has a mass, m, and a height, h, in a uniform gravitational field. I want you to select all of the following that will increase the gravitational potential energy of the object by a factor of 4. This time, I want you to select 3 answers. Select 3 answers. So the correct answers here are C, D, and F. All right, let's talk about a gravitational potential energy when we have a non-uniform gravitational field. So gravitational potential energy, stored energy due to a non-uniform gravitational field experienced by an object. In this case, this is our equation. All right, now once again, U, capital U, is potential energy, and this little lowercase g, always use a lowercase g, not a capital G. Capital G means something different. Lowercase g tells me that it's gravitational potential energy. All right, so negative, capital G, mass 1, mass 2 divided by r. Remember, capital G represents the universal gravitational constant. We have 2 objects here, mass 1 and mass 2, and r is not the radius. It is the radial distance. I talk about radial distance when I go over circular motion and gravitation. So look through that again, okay? R is the radial distance between the 2 objects, okay? All right, more practice. Object has mass m1 and is orbiting a second mass with mass m2. The center of mass distance between the 2 objects in a non-uniform field is r. It's our radial distance. Select all of the following that will keep the gravitational potential energy of the objects constant. All right. 2 answers. In this case, I didn't tell you how many to pick, but in this case, there were 2 correct answers. B and C. B and C. All right. Okay. So if you ever see or hear reference to something called mechanical energy, just think about kinetic and potential energy. All right. Kinetic and potential energy, and potential energy could be elastic and gravitational, are both types of mechanical energy. So anytime we refer to the total mechanical energy of a system, we mean the combined amount of the kinetic and potential energy. So it would look like this. All right. We've got our kinetic plus our 2 types of potential energy. So conservation of mechanical energy basically says you cannot create energy, you cannot destroy energy. You can only change its type of energy. So the total amount of mechanical energy in a closed system is going to stay the same. A closed system means that there's no external net force. No external net force that's influencing or affecting our system. So here we've got our initial mechanical energy is equal to our final mechanical energy. So what I do is I substitute all the different types of our mechanical energy, the initial forms of it, and set that equal to the final form of all the different types of our mechanical energy, set them equal to each other. All right. Now, um, let's modify that equation slightly. So it's exactly the same, except in this case, I've added work. I've included work. So by including work in our conservation of energy equation, we can account if there's any external forces adding energy or taking energy away from our system. So if we're dealing with a closed system, no external net force, then the work involved will just equal zero. I kind of like this equation because sometimes it's hard to know, well, does this is this a closed system? Is it not a closed system? So by including this, I automatically will be taking, I won't have to worry about making that mistake, because if there's an external force or something like that, that's going to show up in the form of work, and I've already included that into my equation. If there isn't anything there, that means that there's no work, and so this part becomes zero and it goes away, and I don't have to worry about it. So I like to do that. Take what you want from that. Let's practice. So a cart of mass m is placed on a ramp of angle theta with a spring constant k at the bottom. The spring is compressed a distance d, displacement d, with the cart right next to it. The spring is then released and the cart travels up the ramp. What is the maximum height that the cart can reach? Now, you're going to have to solve this algebraically, and you are only allowed to have constants and 4 different variables. You can have k, the spring constant, x, the displacement, m, the mass, and then I guess little g is just, that's a constant. All right, so you can have constants, and then the spring constant, you can have the displacement, you can have the mass. And obviously, you can also include the maximum height. That's allowed as well. So pause the video, work some algebra. This is conservation of energy. Look back to those equations, see what you can come up with. All right, moving on. So before I launch into this, a couple things to consider. One, the cart's starting from rest as the spring is released. So that moment that we release the spring and the spring starts pushing against the cart is initially at rest. It's not moving until after the spring pushes on it, all right? At that first moment that it starts to do that, it's not moving, it's at rest. When the cart reaches its maximum height, it's no longer moving. The moment before, the moment after, it's moving, but when it reaches that actual maximum height, it's kind of changing direction, and so it's not moving in that actual moment. That's actually pretty helpful. So anytime I'm looking at a conservation of energy problem, I always start with the entire equation. I write the whole thing out, all of it. Then I go through and I cross out or erase the terms that I don't need. So in this case, the object's not moving when it starts, the object's not moving at the end, so I don't need my initial or my final kinetic energy. Those terms can go away, all right? What other terms do you think we don't need? Well, we haven't really established a zero line, so let's pick one. Let's find something that works. So I am going to set my zero line to be right along even with the cart. That way, the cart's initial height is 0. If the cart's initial height is 0, then there's no initial gravitational energy. So, and this is a closed system. There's no external forces, so we've got no work being done. An example of what could cause work being done, if there was friction being applied, that could cause some work that would take energy away from our system and it would lose energy. However, we're going to assume it's frictionless, so you don't need to worry about the work. All right. When the object gets all the way up to its maximum height, nothing's being stretched or compressed, so there's no elastic potential energy. So that big long equation simplifies down to something very simple, very easy to work with. All right. I always start with the entire equation so I don't accidentally forget or miss something, but often that equation gets a lot simpler. Plus, you're likely to get points for identifying the initial conservation of energy equation. That's often something that they look for in free response style questions that can get you points as long as you set it up correctly, okay? So at this point, I'm substituting equations in, and then I use algebra to solve for my maximum height. This is the answer that you should have gotten. I only have constants and the approved variables. So, ladies and gentlemen, this is what we would call a derivation, all right? There wasn't an exact equation for our specific situation and what we needed. So we started with what we know, and then we used algebra to create a new equation that meets our needs. That's called deriving. You're going to have to derive, guaranteed, all right? Now, something to point out, this maximum height is not the height, it's not the distance that the cart traveled along the ramp. It is not the distance the cart traveled along the ramp. It is simply how high the cart is above our established zero line. That's all. So let's say that the ramp is at an angle of 30 degrees and the cart has a mass of 2 kilograms. The spring has a spring constant of 100 Newton meters, and the spring is being compressed by 0.10 meters. Notice I'm in meters, not centimeters. What would the maximum height be? Well, under those conditions, I now have an equation that I derived, and so it's real easy. I just plug everything into my equation and I get an answer. You should get 0.025 meters, or if you want to express it in centimeters, 2.5 centimeters. All right, well, let's get a new one. What if everything's exactly the same except we double how much the spring was compressed by? So instead of compressing it by 0.10 meters, we compress it by 0.20 meters. What would our new maximum height be? Well, our new maximum height would be 0.10 meters, or 10 centimeters. Now, notice, I had different conditions, but I didn't have to solve my equation again. By solving for it once algebraically, any condition, I can plug different variables into this and I'll always be able to get the answer. I don't have to solve it a second time or a third time or a fourth time. It's one of the advantages of solving for something symbolically, algebraically first before you put the numbers in, all right? All right, let's look at the same situation, all right, but we're only going to change one other condition. So the cart still has a mass of 2 kilograms. Spring still has a spring constant of 100 Newton meters. We're going to say the spring is still being compressed only by 0.10 meters. This time, let's double the angle. So instead of it being 30 degrees, it's now 60 degrees. What would the new maximum height be? Well, hopefully you realize this is almost kind of like a trick question. It's meant to test to see if you understand the conceptual things you need to. But if you look back at our equation, our equation does not depend in any way on the angle. All right? Changing the angle doesn't change that maximum height that it gets to. So it's still going to go to 0.025 meters or 2.5 centimeters. All right? Watch out for stuff like that. All right. So normally what I would do is I'd have some sort of a demonstration in class. However, I can't really demonstrate it very well. I don't have all the materials that I would need or anything like that. So if you go to my slides, if you go to my actual slides in Google Classroom, all right, in the notes for this slide, number 47 out of 50, there's a link. Click on the link and it will show you an image of someone else kind of doing this demonstration. So take a look at that and then answer these questions. First, identify all the different types of energy that are present. Then I want you to explain how the person could be confident that their face will not be damaged by the demonstration. Well, first off, different types of energy. There's definitely some initial gravitational potential energy. All right, that happens throughout this presentation. All right, the other type of energy that you get is kinetic energy because the bowling ball is moving in this situation. Some people might argue that there can be some elastic energy Elastic potential energy, depending on whether you're using a chain or a rope, is it being stretched or compressed at all? That's fair. To make it simpler, we're going to assume that there's no stretching or compressing going on, in which case we would say that there's no elastic potential energy, just kinetic and gravitational. All right. Now, the bowling ball starts with a certain amount of energy, total energy. And at the beginning, all of that energy is just gravitational potential energy. All right. So, conservation of energy tells us the bowling ball is never going to get more or less energy than it started with. All right. As long as there's no work being done on the system, as long as nobody runs up and gives the bowling ball a push or something like that. All right. So, when the bowling ball starts to approach its initial starting point, it has the same amount of energy that it started with. And since gravitational potential energy is based on height, if it has the same amount of gravitational potential energy that it started with, it will have the same height. And we can be confident, even though it might be a little scary, that it's never going to go higher than its initial position. Because if it goes higher than its initial position, that means it has more gravitational potential energy that it started with, and its total amount of energy increased. All right. And that doesn't follow with conservation of energy. All right. Let's look at another demonstration that I can't really do. First, take a look at this image. What do you observe about the two different tracks? We've got a track that's a straight line, shortest distance between 2 points. And we've got another one that follows this different curve right here. Okay. So, which track will allow the metal sphere, or the balls right here, which track will allow them to travel the fastest? Make a prediction. So I have an actual one of these. It's called a brachistochrone. I have one of them, but obviously it's at school. I can't get it for you. I'm allowed on school right now. But once again, go to the slides. If you go to the actual slides that I have, you can click on this link right here and watch what happens. I want you to watch it and try to explain what happens in the demonstration. Try to use conservation of energy to explain what happens. I'm not going to explain it to you here. I want you to work it and try to see if you can figure out a good explanation as to why what happens. All right. So there you go. That wraps it up. This is just a cool little image I found that I liked. It kind of helps put some of the stuff, make connections on how these things relate to each other. But that's it for energy. Energy is one of the most fundamental, commonly used aspects of physics. It is very important to understand. Right now, there's really not a ton into it. We're going on about 45 minutes here, and we've gotten through pretty much all of it. But it's so important to understand. And to be honest, it's a lot easier to work with energy than it is to do something like kinematics. There are some problems that you can solve it with kinematics, but it's actually easier. It's actually easier if you use energy. You just kind of got to look at the situation and see if perhaps that might be an easier way. But anyhow, hopefully this is helpful to you. If you have questions, let me know. Otherwise, have a great day.